Professor, I don't have your voice.
Can you hear me now?
Yes.
Oh, sorry. I was saying that to study what is contained in the group of lectures number 2 and 3, you can use this principle of fluorescence spectroscopy book. Okay? This is a very huge book, more than 900 pages. But if you read the chapter number 1, I show you chapter number 1, that is the introduction to the book. Here it is. This is a sort of summary of the book, and you will find inside all the information that I'm giving you during the lectures. So you can read the introduction and it will be sufficient for you. If there is some topic that you want to study better, you scan the index of the book and you go to the respective chapter and you read a bit more. You can find it. Okay? And this is a book that can be very useful for your future studies. I gave you this book, and there are 3 more books where one can pick up the information. One is the Atkins, Physical Chemistry. I have the copy in Italian, some photocopies, but you can find it around in English because I'm sure that you can find it with torrent or whatever. And if you scan the chapter 17 on spectroscopy, you will find what we have said today. Absorption lines, Frank-Condon principle, the Morse diagram, the Born-Oppenheimer approximation. You can find it in Italian, okay? You see the intensity of the transition line, how it is connected to the wave functions. All what we said today is more or less explained here. There are 2 more books. These are few copies. There are about 20 copies, 20 pages per book. And this is Atomic and Molecular Spectroscopy from Svanberg. Svanberg is another boss in the world about spectroscopy, and he is in the Nobel Committee. Okay? And this Svanberg, you can find the molecular structure, electronic levels, the Morse curves, bonding and anti-bonding orbitals. It explains you the same things in a different way. So you can read the same things explained by another person, and you can somehow integrate the information. So you see the Morse curve, the levels, and so on. And I give you another book also, the Weary, Modern Fluorescence Spectroscopy by Weary. Here, and again, you see that you see the same images, the Morse curves, the Frank-Condon, the transitions, and the shape of the absorption spectra, and this diagram with levels that we shall discuss later on. Okay, so you have several possibilities. Of course, the main material are the slides. All what we say is written on the slides, so you can find it there. But if you need to find it written somewhere, you can review these books. Now, the book from Lakovic I gave you, these 3 copies I will put on Classroom today or tomorrow, whatever. Okay? Now, we can go, let me close. Okay, we can start with the 3rd group of slides. That is luminescence spectroscopy of organic molecules. So, and the fluorophores that are used in the field of life science. Now, what we want to discuss is luminescence spectroscopy, or in general, luminescence, that is studied with an experimental configuration like this. Okay? So think that you have a molecule with a certain energy level diagram. Okay? So with a ground state and two excited states, for example. Think that you have a light source and that you send radiation, visible radiation, towards your molecule, and that the spectrum of this radiation is a delta function at a given frequency. So you have a single frequency excitation, for example, a laser. Okay? Now, let's think that this frequency is corresponding to the transition between the ground state and the second excited state. So the molecule will absorb light and will increase its energy and will occupy the level E2. What does it happen after that? Now, very often it happens that the molecule decides to return to the ground state, because in physics, you always try to go to lowest energy level that is possible. And the molecule can do it, for example, by a transition from the state E2 to E1 and emitting light with photon energy that is h nu, okay? And then from this state, E1, it can relax the ground state by emitting light at another frequency, okay? And if you measure the spectrum of the emitted light, you will see that in the spectrum, there are some lines corresponding to the transitions, okay? So there is an emission spectrum that you measure with a detector, okay? That has got some lines corresponding to the possible transitions, okay? Now, since the emission process involves an interaction with electromagnetic radiation, the selection rules that are valid for the absorption process are also valid for the emission processes. So the transition dipole moment must be not zero. So the parity of the states that you use in an emission transition must be opposite, okay? There must be spin conservation. So you cannot transit from a state with spin 1 to a state with spin 0 and vice versa. Okay, so there are the same rules. So generally, in luminescence spectroscopy, you excite light with a monochromatic light at a single frequency, and you detect light with a wavelength sensitive detector, because you have to know the spectrum of the emission. And normally you measure off axis. What does it mean off axis? You measure fluorescence emission at an angle that is different from the direction of the excitation light. That is clear why. Because surely one part of the excitation light will go through the sample, and you don't want to detect this light. You just want to detect the emitted light. So you make the measurement of axis. Now, we come back to here, to this diagram here, and we try to understand what it may happen. So let's think that this is the ground state of the molecule, and this is, so ground with G, and it is a singlet state. So this is the single state, and it can be split in several vibrational levels. Then let's think that a molecule has got two excited states. These are singlet state, SE1, SE2, excited state 1, excited state 2. They have got the same parity as the state here, okay? But we know that there might be states of the molecule that are triplet states, in which the molecule has got a total spin that is 1, okay? And this, for example, can be the energy level corresponding to this state. We call this state triplet state 1, okay? There could be other triplet states and other excited states of singlet type, but we just make a sketch with few of them, okay? Then let's think that we excite our molecule with radiation of a wavelength or of a frequency that can bring an electron from the ground state, for example, to the second excited state, okay? Here, on top of here, to any vibrational level. Now, in this simple sketch that we marked here, we said that it could be that there is this transition, there is light emission, and then that it could be that there is this transition, there is light emission. This is not true. In reality, in real molecule, the first process that it happens when you have a molecule in such an excited state can be a process in which you relax to the first excited state in a non-radiative way. You see here that for this process here, I'm using a straight line, and I mean with a straight line that this is a transition that is involving interaction with light. So there is absorption of a photon. Here, when I sign this process with a sort of spring here, this spring here is something like a phonon. There is energy. We think that this transition here does not involve light. What does it mean? The energy is not emitted by light, but it is emitted in terms, for example, of vibrations, of heat. Okay, the molecule loses energy by some other mechanism. Otherwise, the other process that may happen in a first simple description is that the molecule relaxes to a triplet state. And you will say to me, but professor, you said us that transitions between singlet and triplet states are forbidden, okay? No, I said that for molecules interacting with light, transition involving light cannot happen between singlet and triplet. But this transition here is a non-radiative transition, so it doesn't obey any selection rule, okay? We told this somehow. So when you excite a molecule in a highly excited state, the first thing it happens is that it relaxes either to this state here or to this state here, okay? Now, what does it happen if the molecule relaxes here? It will go to the lowest vibrational level, so it will dissipate energy by means of vibration and then get here. And from here, what will it do? It doesn't like, the molecule doesn't like to have extra energy. It can transit from here to the ground state by emitting light. And this process is permitted because the spin is preserved and maybe the parity of the two states is opposite, okay? This process here is named fluorescence. This is named fluorescence, okay? And normally it is a process that happens very quickly. We will give the time scale later on. Now, If the molecule relaxes to the triplet state here, then it can emit light and relax to the ground state. But there is a problem. The problem is that you are in a triplet state, and the transition to the singlet state is forbidden for light emission. Sorry. So in principle, this process should not be permitted. But the rule that says that you cannot transit from singlet to triplet state is true only for very simple systems. But if you have a complicated molecule with a very, let's say, large structure, then there can be a weak spin-orbit interaction, and the spin-orbit interactions breaks the rule, and you have a small probability to have such a process. Okay? So you can make this transition, and this process here is named phosphorescence. Now, what is fluorescence? When do you see fluorescence in your real life? And when do you see phosphorescence in your real life? You see fluorescence when, for example, you take your notes that you are taking on the exercise book, and you use an highlighter, a yellow highlighter. Then that highlighter is a solution of fluorescent molecules inside a liquid. You scratch your book, you leave the molecules on top of the white exercise book, okay? And what does it happen? Blue light or violet light for the lamps hits your molecules, bring them to an excited state, then they make this cycle here, and then they emit light in the yellow, or in the red, or in the orange color of the highlighter that you choose. For any color, you choose a different molecule inside your highlighter. That is fluorescence, and it is almost instantaneous as a process, okay? What does it mean? It means that if you switch off the light of the lamps, okay, and you look at your exercise book, you don't see yellow light coming from this line, okay? What is phosphorescence? Phosphorescence is what it happens when your grandfather and your grandmother, when you were 6 years old, made you as a gift those little stars that are colored in green that you attached on the roof of your room, okay? And when you were going to bed, you were switching off the light of the lamp, so there is no excitation light from the lamps. Nevertheless, you see on the roof these nice shining stars. This happens if you go to Pisa and buy a reproduction of the Tower of Pisa that is stained with such, or if you go to Tehran and you buy a reproduction of some very important mosque, and normally they are painted with a paint that then emits light when you go in the dark. This is what you have got in your watch. If you have ancient types of watch where there is this phosphorescent material on top of the hours, okay? Now, why is there a difference between fluorescence and phosphorescence? The difference is that this process is permitted. That means the probability is large. So when a molecule is here, it is very probable that it will emit light, and it will do it very quickly, okay? So fluorescence is very quick. The phosphorescence process is a process that has got a very low probability. So there is a low probability that the molecule will emit. That means that the molecule will wait a long time before emitting because the probability is low, and so it is a delayed process. Okay? So normally the singlet transition gives rise to fluorescence, and the triplet singlet transition gives rise to phosphorescence. Both of these processes are luminescence processes, so be careful. In physics, luminescence is the sum of two types of processes, fluorescence and phosphorescence, okay? Now, when you speak of emission, there is a quantity that is very important that is named the fluorescence quantum yield. Yield, it means a gain. How much to yield means how much you gain, okay? And it is defined as it follows. The quantum yield is number of photons that are emitted divided by the number of photons that are absorbed. Okay? So when you have an emitting molecule, okay, you define the quantum yield like this. Be careful. What does it mean that the quantum yield is 1 according to this formula? That it means that if you absorb 1 photon, you will emit 1 photon. Be careful, this is not an energy balance, because here you emit 1 photon, absorb 1 photon, and after this process, you may emit 1 photon. And if the quantum yield is 1, it means that for every absorbed photon, you have an emitted photon. But be careful, the energy that you emit is lower than the energy that you absorb, because part of the energy is lost here in this non-radiative decay. And the energy of the emitted photon is lower than the energy of the absorbed photon. Is it clear? So if you have a molecule that has got quantum yield 1, it doesn't mean that it gives back all the energy that you gave her. She always gives back less energy than you give her. Okay? So when you use a highlighter on your exercise book, you see some intensity coming from the yellow strip that is on your book, okay? You see this intensity. What is this intensity depending on? So how bright is this strip that you have on your exercise book? Clearly, the brightness depends on the fluorescence quantum yield. If the molecule that you are using in your highlighter has a fluorescence quantum yield that is 0, what does it happen? They absorb light and they do not emit light. So you don't see any emission, okay? But of course, the intensity of the emission process will also depend on the absorbance of the molecule at the excitation wavelength, okay? If the molecule that is in your highlighter absorbs in the ultraviolet at 350 nanometers, and if in the light coming from the lamps, there is no light at that wavelength, you cannot excite the molecule. And of course, even if your quantum yield is different from 0, you will not see any radiation. And of course, the intensity of the emission will depend on the intensity of the excitation radiation. If you double the intensity of your lamp, your highlighter will emit double the light because you send more excitation light. So in general, the intensity of this radiation that is emitted depends on the fact that your molecule absorbs at the excitation wavelength. Depends on the quantum yield, and it depends on the intensity of the excitation, how much photons per second you send. Okay? Now, can I stand up? What is the difference? Can you see me? What is the difference between the molecule that is used to produce this paint here, okay, and the molecule that is used, mi dà l'evidenziatore, that is used to produce this highlighter here. What is the difference? This is red, but I don't see any fluo effect, okay? This is yellow, and I know that this is fluorescent, okay? I am acquainted. What is the difference? Here, I'm using to stain the paint, to produce this paint, some pigments, some molecules that absorb the blue and absorb the green. So light coming from the lens that reaches the bottle, light in the green and in the blue is absorbed. The molecules here, they do not absorb the red, and the red light is scattered around, is diffused around, and I perceive the scattering, okay? The same way, this ring here is colored with molecules that absorb red and green, and they do reflect the blue, okay? So this is a pure absorption process, okay? Here, that's different, because light in the, I don't know, blue-violet is absorbed by the molecules, and they do emit in the yellow. So my eye sees more yellow than I would see if there is only the absorption. I have the effect that there is more yellow because there is fluorescence from the molecules. So in this case here, the molecules absorb, but they do not emit. Their quantum yield is 0. They do not emit. In this case here, the quantum yield of the molecules is different from 0. Probably, since I want to produce efficient markers, the quantum yield here is almost 1. It's a very good molecule. Okay? So, in your shirt, there is a dye with quantum yield 0. It absorbs the red and blue. In his shirt there is a combination of pigments that are absorbing all over the spectrum, okay? Because it is black. It's absorbing everything and doesn't emit anything, okay? In my shirt here, most of molecules do not absorb light that looks like white with some blue because there are strips. That's clear to you? So the quantum yield says whether a molecule is fluorescing or not. Okay? So this is the definition, so the fluorescence quantum yield. We can take one particular molecule in this spectra viewer software, and this is its absorption spectrum, okay? So the dashed line is the absorption spectrum, and you see that the absorption spectrum is characterized by some peaks, maybe some vibrational replicas, no? And this is here, marked in green. This is the emission spectrum. So that's the spectrum of the light that is emitted here. Okay? As you see, this is wavelength. The molecule absorbs in a range of wavelengths between, say, 300 and 420. So it absorbs at a certain energy and it emits at a lower energy. But lower energy means longer wavelength. So the emission spectrum is a longer wavelength. It is shifted here. And also the emission spectrum is characterized by some peaks that you can even distinguish here. You cannot distinguish them. Okay? Now, for almost all molecules, it is possible to have absorption from the ground level to different excited singlet levels. So you can go from here to here or from here to here. Where it is written in this spectrum here, you can have absorption here, but for example, you see that the spectrum here is growing again. It is outside of the measurement window, but probably there is another peak here. Okay? So if this absorption peak corresponds to this transition, the absorption here, that is at a shorter wavelength, so at a larger energy, corresponds to this transition here. Okay? Now, what did we say? We said, look, if you excite a molecule to an excited state, the first thing that happens is that it will relax here and then emit light. Okay? This happens even if I excite to a larger energy level here. It will relax down here and then emit. Experimentally, this can be seen in the following way. If this is the absorption spectrum and you send light at this wavelength here, you excite the molecule this wavelength, you will measure this emission spectrum. If you send light at this wavelength here, there is absorption, the molecule will absorb. Nevertheless, even if you excite to a different wavelength, you will measure always the same emission spectrum. Because this emission spectrum here is governed by the transition from here to here. And even if you go here, the emission will happen from here to here. So what you measure experimentally is always the same. Okay? Therefore, if you take your marker, and you send a violet laser, you will see that it will emit yellow light. If you send an ultraviolet laser, you will always see the same emission light, the same, because there is this relaxation. Now, this process, the fact that the emission has always the same spectrum is named Kasha rule. So radiative emission takes place only between the first excited state and the ground state. And there is here it is explained the reason why it happens, but I don't want to explain it now. We will go back to this later on when we will discuss more in detail some other processes. Okay? So later on in the next 2 slides that we will discuss probably next time, we will explain why the Kasha rule is valid. Now, and this is probably the last, yes, the last 2 transparencies. What did we say? We said, look, when I have absorption, I can go from here to here, or to here, or to here, or to here. So in the absorption spectrum, I will see several absorption peaks. Okay? Now, what does it happen when I have an excited molecule that is in this state here? Okay? it can relax to any of the states that are here. It can go from this electronic state with vibrational level 0 to this electronic state with vibrational level 3 or 4 or 2 or 1 or 0. It can relax to any of this. Of course, the probability to relax to the second or to the first or to the 0 level will depend from the superposition of the two wave functions. And again, you see that the superposition of this wave function with the wave function number 2 is better than that with the wave function number 1 or 0. There are intensity probabilities. Therefore, when I measure fluorescence, and I remember why is this energy? Wait a moment. 01, 02. This is energy, of course. And when I measure fluorescence, I see that the fluorescence emission is constituted by some emission lines. And these lines correspond to the transition from this state, for example, to the state here, 0. And the energy difference between these two states corresponds to this 0 phonon line that we gave before. If instead you relax from this state to the state number 1, the energy of the photon will be smaller because the energy transition is different. And you will see an emission that is a lower energy here. And so on. Each transition corresponds to a different energy or to a different wavelength. And the intensity of these emission lines, they are the same as the intensity of the absorption lines because the superposition of the wave functions is the same. So the probability to have 0-2 transition is the same as the probability to have the 0-2 transition in the emission case. So that these lines are symmetric. Look, this is really true only if the two potentials are parabolic. In reality, if the shape of the Morse curve is different from the singlet 0 state to the singlet 1 state, there should be some differences, but we made the approximation to have parabolic potentials. Okay, so therefore you will see an emission spectrum that is symmetric with respect to the absorption spectrum and symmetric with respect to these 0 phonon lines. These are, where is it? So the shape of the emission spectrum is exactly similar to the shape of the absorption spectrum, but reversed in energy. Okay? And this is what you observe experimentally. That, for example, for the case I've shown you before, oxazine 6G, the absorption spectrum is like this, the blue curve. It is the same we have shown before. And absorption takes place above 1.8 electron volts. And the emission spectrum has a shape. This is a measurement that I made myself. That is a replica of the absorption reversed with respect to absorption. You see there is a mirror image. Now, these two curves were obtained, these are fluorescence curves, were obtained by exciting oxazine at two different wavelengths. So when I excite it here in the red, I see this spectrum here. And when I excite here at a longer wavelength in the peak of this curve here, I see the black curve. The red and black curve have the same shape. This is due to the Kasha rule. The only difference is that the black curve is more intense than the red curve. And why is it more intense? Because here the absorption is larger than here. So if the absorption is larger, I excite more molecules. Okay? So the two spectra are the same and the intensities are different. So in organic molecules, if you plot the absorption spectrum, and be careful, this is wavelength, whereas here there is energy. So this is a graph in wavelength. The absorption peak is at a wavelength that is smaller than the emission peak. Okay, emission takes place at a longer wavelength, so a lower energy. And this peak separation here is named the Stokes shift. Okay? So the Stokes shift in absorption spectroscopy is the distance between the absorption and the emission peak. Okay? Now, be careful. Here, the first line here, the zero phonon line, so you can have a process in which you absorb from here to here and you re-emit to the same level. So the absorption and emission lines, they are at the same frequency. There is no Stokes shift. Where is the Stokes shift coming from? From the fact that the intensity of these lines is symmetric and different. And then you have two spectra that are dominated by one line that is probably is not the 0, 0 line, but here, for example, is the 0, 2 line. And between the 0, 2 and the 2, 0 line, there is an energy difference. Okay? So the Stokes shift is due to the difference of the transition probability between the levels. And with this, we stop here. And next time, we resume this information with the so-called Jablonski diagram that takes inside all the processes that we can meet when studying a process. For the moment, we discussed phosphorescence, we discussed fluorescence, but we have to discuss some other processes, okay? And in particular, non-radiative processes and first resonant transfer. So we stop here and we meet on Thursday morning at 9 in the hall number 3. Okay?